Good morning, everybody. Yeah, that's not a bad outcome after the day yesterday night. I think that we should be happy with that. Okay, this is not a science talk, as you would expect. I'm trying to tell you something about the marketing of synchrotron radiation and its marketing to industry. If you are long enough in that business, you know that you have to do also marketing to politicians. But that's a different talk. You have to convince politicians how important it is what we are doing, and that we are saving the world, minimum, I would say, and they have to put money in. In this case, I'm trying to tell you something about how you can convince industrial partners, which is an important business. Okay, in principle, I could stop my talk here with the first slide. It would be very easy, because there is no silver bullet. That means we are working for the last 50 years in that business, and we are trying to convince industry. And if there would be a silver bullet, then everybody would use it, and there would be no talk. It's not necessary, because we would all use the same technology. You will meet other people, Alexandro making the same business, the lady from Diamond, Elizabeth is here, and you will learn within that next few days something about how to do it. But the summary, if we are really truthful, is there's no silver bullet, and you have to do it perhaps individually. Okay, that means what I'm doing is I'm telling you something about my own experience. That means then perhaps you can learn something or not. It's a little bit up to you. Okay, we started actually doing synchrotron radiation with industry in 1989. I suppose that's long before most of you were born. So, and then we started, and we have written already our first review article. That's examples for the industrial use of synchrotron radiation already in 1992. That was very, very early. That means we have a lot of experience, and I'm showing you in the next slide what I did in the last 40 years or so. I started that business collaborating with industry at Bonn University. We have in Bonn, as most of you might not know, we have a long tradition of operating electron accelerators, synchrotron, storage rings, whatever you would like. And Bonn University was the first facility actually in Europe, which people don't know, that used synchrotron radiation for experiments, very, very early. Okay, because it was university, it's a little bit tricky to do industrial work, and we had to find a compromise, because my colleagues were not too excited. They were always a little bit afraid. Industry is determining what we are doing here. What is the freedom of science? And what the compromise was, we tried to do 1/3 of our beam time for industry, industrial use, and 2/3 for basic research. And that was a reasonable compromise. I learned a little bit about the business of research in industry, because I spent half a year part-time in the Bayer Research Lab in Leverkusen. That's very close. It's 30 kilometers away from Bonn. And I learned that researchers in industry are thinking slightly different from what we are learning in academia. I'm coming back to that in my talk in the afternoon. You are invited for my second talk. There's a different Christian name, but I will talk about that problem later on also. Okay, in 1999, I switched sites. I went over the Atlantic, and I was at the Center of Advanced Microstructure and Devices. It's a small storage ring in Baton Rouge in the United States, owned by Louisiana State University. That's a public university, and that was a real problem, because public universities in the US, they are very bureaucratic. They might have learned that business in Germany, I'm not really sure about that, and they optimized it. And getting all the signatures from industry, that means starting with a quote, and then the department chair has to sign it, the provost has to sign it, the chancellor has to sign it. We did some work with BASF in Baton Rouge, because all the chemical companies, they have some production in Louisiana because of the Mississippi River. And they told me, if there's one more signature necessary, that's the end of our collaboration. It was really a problem also. Then in 2008, I went actually to the Canadian light source, and that was a completely different story, because that was not just beamline scientists collaborating with industry. There was a dedicated group of scientists for collaboration with industry. We had 7 scientists, actually with a director as a lead in that group, for industrial collaboration. And what we established during my time is we hired 3 specialists. We had a specialist for protein crystallography, which is was at least a flourishing business at that time. We had 1 specialist for agricultural research, and we had 1 for mining. Why? Agricultural business and mining are one of the pillars of the economy in Canada. And we said let's focus on what is really important for Canadian industry, and therefore we said agriculture and mining. And that agricultural research was quite successful. I'm coming back to the next slide. Today I'm a hobby researcher, and I'm doing still a little bit of collaboration. My last industrial partner was actually Michelin, the tire company. Okay, most of the work that I'm doing with Professor Prange, who will cover the second part of this talk, and he will tell you a little bit about the science that we are doing together also. Okay, now, agricultural research. That was established during my time at the Canadian Light Source, and it's quite successful. That means at this point in time, there is a group, what is called the Pan American Light Sources for Agriculture. It means there are 3 facilities: the Canadian Light Source, the Cornell High Energy Synchrotron, CHESS, and the Brazilian Synchrotron. And they are collaborating together in a group called PALSA, and they are doing together agricultural research. There is, until now, nothing comparable in Europe, but we are working on it. We started yesterday. Perhaps we can establish something also in Europe. It seems to be quite successful. Okay, the next point is, when I'm talking about collaborating with industry, what does that really mean, industry? It's a little bit vague also. If you look into what politicians say or politics say, there are 3 different sizes of industrial enterprises. One is the big companies. Big companies are, by definition, companies that have more than 250 employees. Then there are medium-sized companies between 50 and 250, and small companies, less than 50, from 1 single person to 50 or so. That is what politics is talking about. And when we talk about industry, and if you talk to politicians, what is important for them is very often these 2. That means, what are you doing with the medium and small-sized company? That is very often their question. And the next question is, what about the cash flow? That means, how much money is coming into a synchronous reaction facility from industry? My normal answer is, that is not the most important thing. It looks nice because you can prove it directly. But what our experiments are doing for industry to improve their products, to make them more competitive, to educate young scientists also, that is not covered by cash flow. For example, if we help a company, let's say a tire company, to make a better tire by optimizing vulcanization, there could be a significant impact from that, and they paid something like 50K for the research. That means it's not a balance between the cash flow to the facility and the economic impact. But it's very difficult to measure, and there are hardly any publications. There is from the UK an interesting publication about how important Daresbury, that's an old UK facility, how important Daresbury was for the economic development in the UK. If you have a chance, and if you can't sleep at night, please read it. Okay. From my experience, the real customers for collaboration with our labs are the big companies. Dot. Politicians don't like that statement, but that's my experience. Why is that? The small and medium-sized enterprises, that is what we use in the United States, SMEs. The SMEs, they have in many cases what I call no scientific background. Because it's a small company. If you have 10 people, you don't have a research unit. If you are lucky, you have someone who is a physicist or a chemist. But in many cases, they are doing just production. That means there's no scientific background. And the problems are, sometimes they have a problem, but they are not describing that problem in words that are easily understandable to someone in science. That means they are not asking the right question. You would normally ask is, what is the valency of that atom in a compound? That word valency in a compound is for a small business owner, strange. That means you can't discuss that. And in the same way, if you have an answer and you cannot tell that answer in very simple words, they can hardly handle that answer. And that's also a very important point. For these small businesses, our full cost calculations are very difficult. That means if they are paying something like 800 euros per hour or so, plus data evaluation or so, they say immediately, thank you. That's too expensive. There are ways to overcome that. I'm coming to that point in my talk in the afternoon. That means how to deal with those companies also. Okay. What are the general problems of marketing? The problems are always, I would say, the same. That means in many cases, people in industry, also scientists in industry, they don't know about specific techniques that we are using. When you are at a university, also today, synchrotron radiation-based techniques are not standard program. That means you are not learning X-ray absorption spectroscopy. You learn Fourier transform and you learn X-ray diffraction. That is standard or so. But what we are doing, for example, element-specific tomography, that is something that you don't learn also. It means there are difference. That means also scientists in industry, they don't know those specific techniques. That means X-ray absorption and, for example, element-specific tomography and a few other things that are typical for what we can do with our facilities. Scanning the energy of X-rays, for example. Okay. The next one is people in industry are sometimes afraid that it will take too long to get a reasonable answer. I'm also coming back to that also. That is mainly connected to university research, because in the good old days, the professor said, okay, I am hiring a grad student. You will get an answer in 3 years if you are lucky. That is not what industry wants. They want sometimes answers yesterday, not tomorrow. If there's a problem in production, you need an answer immediately also. It means there is a problem there. I'm also coming back to that. That is another issue that non-university labs are dealing with. In most cases, scientists in synchrotron radiation labs are not experts, and they don't have a scientific reputation in all fields. That means if you are a well-educated beamline scientist, you did your PhD in soil science, and that's good. But what do you really know about polymer physics? And that's sometimes an issue. That means dealing with the companies and having the right words for them, the industrial partners. Okay, then there are some issues about confidentiality. We are dealing with that. And again, also for the big companies, the techniques are quite expensive. All right. That's another summary. The easiest marketing for synchrotron radiation is no marketing. And that means, in principle, if you know the right people in industry, you don't have to do any marketing. You just call the guy and said, do you have a problem or so? The other way around is the same. That means if the right people in industry know you and your research, the right people are, for example, former grad students. That's the way it's done very often. That means one of your grad students is going to industry. And he has a problem, and he knows, oh, my former boss, he knows how to deal with that. He's calling you, and you have a collaboration. That's very, very often the case. And therefore, a lot of that industrial research is still done via university professors. That means they know how to use synchrotron radiation. They have cheap slaves, grad students. That means also the costs are lower. The costs are lower than doing synchrotron radiation. And also the word of mouth. Don't underestimate that. If you are in business and people are talking to each other, then you find something like that. Okay, that's the advantage of professors. I mentioned that. And I have to admit, my first collaboration with industry came actually from something like this, because I was at a university, Bonn University. One of the first things that we published was the structural analysis of sulfur in rubber. And you can see the authors, and this guy, Klaus Sommer, he was a grad student in my group before he went to the Bayer company. And he was in the polymer, in the rubber department. And they had a problem, and he said, oh, my boss, he can do sulfur spectroscopy with his setup. Let's collaborate. And that was the beginning of that collaboration. Leverkusen is Bayer, the Bayer company. It means one of my former grad students started that first initiative with industry or so. Okay, now I'm coming to more general things. What should you do to get people from industry interested in what you are doing? That means the first thing that I'm saying is attending specialized conferences. What we are normally doing, we are attending the annual meeting of the Spanish Physical Society. I suppose that most of you are doing that. And I'm attending the meeting of the German and the American Physical Society. That is nice, that's interesting, but people from industry are not attending those conferences. That means in most cases not. What they are doing is they are attending the specialized conferences from their field. And if you go to the literature, if you are really interested, you will see that there are specialized conferences in more or less all fields you can imagine. For example, that is an international rubber conference, a silicon rubber world summit, an elastomer conference, and also a K that is for caoutchouc, a trade fair in Düsseldorf. You should go to those conferences and, if possible, give an interesting contribution there. That is where people from industry, you get attention from them. That means at the American Physical Society, there are hardly any people that are dealing with rubber. All right, it's going on. That means I know that Alba has a focus in building materials, concrete also. Of course, there are, of course, these conferences on concrete construction, or a conference on concrete structure and concrete technology, but it's going on. It's also here, it's a conference on animal health and nutrition, that what we might talk in the future. That means those conferences exist for more or less all areas, and they are attended by people from industry because there is an exchange on the state of the art in what they are doing day by day. Okay. The next point is the same direction. What we are learning in university is you have to publish your results in Nature, in Science, in Phys Ref Letters or something like this. But people in industry, they are not reading Phys Ref Letters. What they are reading when they are drinking coffee is what I call these coffee table journals. And I have 3 of those. For example, this is a coffee table journal for rubber research. It's called Kautschuk Gummi Kunststoffe. There's another one called in food technology. There are sometimes scientific articles, but there are also Sudokus or something like this. In Phys Ref Letters, there are no Sudokus also. All right, and that is something about animals also. That means there are a lot of those what I call coffee table journals, and try to publish an interesting article in those journals. And then you have a chance that people in industry are reading them. Okay, this article that I mentioned, that was published in a coffee table journal in Kautschuk Gummi Kunststoffe. All right. there are two issues. One issue is it had really a strong impact because after it was published, two other companies contacted me. That was Hüls, that's a German company, and Goodyear, both tire companies, because they were interested in what can you actually do with your technique or so. And that's also interesting. A cosmetic company contacted me. I'm coming back to that. The other issue is I could not include it's something like peer-reviewed. I could not include this in my normal publication list because my colleague would have asked me, where are you publishing? It's not first rev letters or something like that. What is the impact factor of this journal or so? That means I took it out of my publication list. Today I can afford. I think I can talk about those issues. But it was really an issue at one point in time. I left it out when I applied for other jobs or so. All right. This was interesting because after this paper was published, L'Oreal contacted me because that sulfur-sulfur bond that's important for the rubber technology is also important for your hairs. You have keratin in your hair, that's a sulfur-sulfur double bond, and if you are tanning, coloring your hair, you are breaking it. I think at least the ladies in the audience might know about that problem. And L'Oreal, they were claiming that they developed a medication, quite expensive, to repair those double bond breaking. And they said, can you actually measure hairs before and after the treatment? The problem is they expected at that point a spatial resolution of something like 10 micrometers, and at Bonn universities we had no spatially resolved opportunities. That means I couldn't do it, which is a little bit a pity, because it would be a very interesting collaboration based on an article in a coffee table journal for rubber technology. All right. Okay, what you can also do is to sell things to industry is you can organize specialized conference contributions and, oh no, what is the problem? If you go to those conferences or if you publish things or so, you need some knowledge and some expertise. That means you have to focus on an area. That means as a beamline scientist, you cannot publish something in food technology, in rubber technology, in polymer, in pharmaceuticals. It's a little bit tricky, and the question is, should an industrial research unit at a synchrotron reaction facility try to focus on a few areas which are important for the economy of the country, and that might be then a little bit easier. And my recommendation is at least some specialization in specific areas can be useful, or you have close collaborations to suitable research groups from university. That also helps if you can trust them also. Okay, the next thing is similar. That means go to trade fairs. German universities, they are going normally to the Hannover Trade Fair. That's a big one also. And there is one hall just for universities. That means we are showing what we can do there. That is a waste of money. I was there several times because I was the leader of the Bonn Technology Transfer Group for the university also. That's a waste of money because there are too many people from too many areas and it's not really focused. Again, it's much easier, much more effective to go to trade fairs, for example, on plastic. And what I said is there is one in Barcelona. Perhaps I can come back in June because there is one trade fair on polymers. And there is actually on agricultural research something in Poland. Perhaps I should also go to Warsaw to be a member of that group there. Okay, the last thing, what you normally can do is you can organize seminars at big companies. I did that. We gave presentations at BASF, at Hüls, at Siemens also. With the big companies, that's possible because they have a research unit. There are something like 50 scientists that are interested or not interested, or at least you can give talks like this. This was not successful, at least not in Germany. That means organizing workshops for some dedicated research areas, for example, on building materials or catalysis, and inviting researchers from different companies. We tried that, but it was not successful. We are not really sure why not. It could be that they were afraid of the direct competition, because the competitors were sitting in the same hall or so. I'm coming back to that a little bit in the afternoon in my second presentation. Okay. summary, another summary. What is really important, my feeling is you should choose what we call a targeted approach. That means rubber industry is not interested in concrete research. That means if you want to have collaboration with rubber companies, you should sell something that has to do with rubber, if you publish something or to go to the right trade fair. What is also sometimes important is showing convincing, realistic examples. That means after we published the first paper, more than 30 years ago, I'm still collaborating with tire companies because they say, oh, this guy knows what we are doing, and therefore they are contacting me from time to time or so. Showing competence, same, and dependability is also important. And that's also important is be realistic in what you are promising. Because sometimes they are expecting miracles. They say, oh, if you do, let's say, an X-ray absorption spectroscopy, that will solve all our problems, which is not true. It means what I'm normally trying to tell them is, let's do a test experiment, and we are doing test experiments for free very often also, and let's see if there is a chance that we can help you to answer your problem. Because the expectations are sometimes too high, but synchronous experiments don't answer all questions. Always keep that in mind. Okay. That was the first half of my talk. Now Professor Pranger is taking over. That's now physics coming after politics. He will talk a little bit about what we did together, I suppose, in the last 25 years in more or less applied research.
Yeah, good morning, everyone. As you might know or remember from yesterday, I'm not a physicist, but my idea is how to talk to industry. Okay, you can understand me? Yeah? Okay. My idea is I'm talking to them what I'm doing. I'm telling how synchrotron radiation-based techniques might help to solve my questions, which come from biology, agricultural research, food science, and so on. And I would like to give you a very brief overview what we did in the last years in this area, and then when I'm talking to them, I try to attract them to be enthusiastic, what I have learned using these techniques, and then I say, okay, I'm not a physicist, I have only a basic knowledge on that, but I have good collaborators, Dr. Hormers, my friends here, and at Solaris, and that is also a good deal to get in contact with people like this. So my research focus is what I'm doing in microbiology. At this, just one sentence to that: food-relevant molds and mycotoxin production, antimicrobial and antifungal agents, especially essential oils, and also the effects of metals, sometimes heavy metals, on bacteria and on molds. And that is a connection between the second part of my research focus is application of Zein spectroscopy in these applied systems. In the last years, we had different collaborations with industrial partners. Just a few examples here. I do not want to go into detail because of confidentiality and things like that, but you see sulfur and zirconium in glue. It's a very small enterprise in Essen. And for example, the head of that company, he's a lawyer. And he is selling glues all over the world in Africa and things like that. And then he asked, I have a problem when selling glue to Africa. It's hot, it's humid, and they sell the glues which are responsible to stick the papers on flasks, on beer flasks and things like that. And he had a problem with that glue. And he had no idea what is in it. And then I asked him, what is in the glue? And then he said, yeah, we are putting zirconium in it. And I said, why? I have no idea, but we are doing it for 40 years. And that was, of course, the idea to think, maybe we have an idea where this zirconium is connected or sticking to. And then I discussed this with Dr. Hormers, and then we had a very nice and small project. And after doing some measurements in that case, and also we looked at the sulfur KH, we were of the opinion, you can get rid of zirconium. It has no effect at all. That did not solve his problem with his glue, but he saved a lot of money because zirconium is expensive. So that is one example, a small one, 10K or something we earned with that and it was a lot of fun. We looked at sulfur speciation in bitumen, in raw oil for a shell company, siloxane degradation by bacteria at the silicon K edge. Maybe Haritsu Maki, who will be present here on Friday, will say something to that project, because he was the industrial partner and he is also one of Dr. Hormer's grad students. He also went to chemical industry, and that was that was a way back. Can you activate it again? Okay. And another connection to a company very close to our university is Renuslup. They are working with lubricants, and also sulfur plays an important role for the elasticity and things like that. In basic research is not is always connected with applications. That is what we did in the last years. And we started with bacterial sulfur globules, understanding how bacteria are able to store sulfur inside to build sulfur globules to oxidize sulfur. That is where we started at that time in Bonn. I'm a microbiologist, but it's for me like eating a little bit honey. I had physics only as a minor. And then I came in contact with this technique, and it's eating the first spoon of honey. And later on, you want a little bit more. And now in the last years, we continued our work, and we investigated, for example, onions, coffee beans. That was part of Henning's PhD work. Selenium speciation in Canadian lentils, because the soil in Canada contains a lot of selenium, and selenium is an essential element for human and also for animal nutrition. We were interested in cadmium speciation in chocolate. We investigated sulfur in wheat gluten proteins, and I printed this in bold because after summary, I would like to go a little bit more in detail in this topic, sulfur speciation in wheat gluten proteins and the influence of molds on these proteins. We were interested in rust fungi, soybean rust, wheat rust. We investigated microbial mats, which is connected to geomicrobiology. Very recently, action of silver and copper ion against human pathogenic bacteria and the use of ions as disinfectants. It is well known for 2,000 years that silver has an antimicrobial effect, but the way or which part of the silver, okay, it's a silver ion, but it's more complicated in copper, because copper has two valencies. And there are some experiments, very fundamental research, but exactly showing which part of the copper is working against or is antimicrobial. And we also gained some information, because silver is much more effective. Copper is more or less, just there's another electron, it's more or less the same element. So this is also apart from the basic area. Selenium tellurium speciation, and very recently, together with Susanne von Ameln, she will come today in the evening. She is a lawyer, and you will see at the end, it's my second example, you will see how synchrotron radiation also might so-called interact with lawyer problems. So selenium speciation in selenium-enriched bottom mushrooms. Lead uptake, copper accumulation in yeast, phosphorus acid in coke. That was just a joke experiment. You know, there's phosphoric acid in it, and we were of course able to measure it, but we were happy to measure at the phosphorus K edge at that time. Just we tried to put coke in the beamline. Arsenic speciation in blood feces, urine samples of rats was in collaboration with colleagues from Canada, and we just recently started to investigate zinc at Solaris at the Astra beamline together with Jonathan Riedmüller, who's also here in the audience, because his topic of his PhD thesis is digestion in pigs, and zinc is also a very important element in that area. So in summary, we measure everything that does not resist. We are trying everything and going ahead. Now the two examples. The question was, how do oxidizing agents, which are often used in bread making processes, how do they work and how do they interact with the so-called gluten network, the gluten proteins, which are responsible for elasticity and things like that in doughs. Wheat gluten proteins, you might know them from celiac, this part. So, and the second part was how do molds interact with these gluten proteins? So they determine the elasticity of the flour and of the dough because there's a special ratio normally between SH and SS bonds, and there's some interaction in the gluten network. So it's in principle a three-dimensional network, and the so-called low molecular subweight units, they are connected by these disulfide bridges, which we call disulfanes, and in principle it's a polymeric structure in an intact wheat gluten, and it's very comparable to the sulfur structures in the bacteria and also in the tires. So nature always works with more or less same principles, in this case at least. So the disulfide bridges are most important. We recorded the spectra of these subunits, and we compared it, of course, with suitable reference compounds. And what you easily can see here, when looking at sulfur K spectra, you have here the energy range, and you see important peaks here at high energies, which is always an indication of oxidized sulfur compounds. And what we found when using iodide and bromate in bread making, we easily could show that higher oxidation states, higher than disulfide bridges, are easily detectable, and in this case, as soon as they have oxidized to higher oxidation states, they do not contribute to the gluten network. In bread making, it's a problem, but if you want to make special cookies, for example, we have in Germany these small and flat Leibniz cookies. They are very dry, simple cookie. Then it is intended that these disulfide bridges do not contribute to the baking product, and in comparison for a muffin, for example, you would like to have a big one and not a flat cookie with it. So important is the ratio and the occurrence of disulfide bridges. If you perform baking tests, for example, so you have here a baking test which was performed at the University of Munich at that time. We have here, in principle, it is the same dough, but this one was before contaminated with different molds, Aspergillus and Penicillium. And you can see if this wheat on the right side is contaminated with these molds, the baking quality is very low. And so the question was, can we see this effect also using the spectroscopy? We expected that there is also an oxidation to higher oxidation states, mainly to sulfonate at this point. And we found some differences. As microbiologists, we are always trying to use different molds on the flour. We also made some experiments with fusarium. They are not able to oxidize SS bridges to higher oxidation states, so they do not lower the baking quality. So there are differences in molds, and we connected it, of course, with experiments which we do in microbiology. We determined different species and genera of molds. We proved the development of these molds also with molecular biological methods, with PCR reactions. We followed the concentration of mycotoxins, and this was really in the corresponding trials in very good order, together with what we gained from, what we gained from the results of the spectroscopy. So this was one part, not only using the molecular biology and the chemical techniques, also a biophysical technique to understand the whole system, how molds interact with the gluten network and also chemical agents interacting with that network. And the second example is how is selenium accumulated in selenium-enriched button mushrooms Agaricus bisporus is a famous one, which we call champignon in Germany. So button mushroom, you have the brown ones and the white ones. And also in salinized yeasts, which is often used as dietary supplement. So, and in general, only biological available, organically bound selenium can act and can be used as an essential trace element by human beings. So it's not a good idea to eat pure selenium, gray metal selenium that is not working. You need the biological form of it. And yeast and mushrooms can accumulate the selenium mainly by uptaking selenite and then oxidizing it or making a bridge to an organic compound. But it was not really clear how it is really accumulated and what is the exact chemical form. So, and we used this one. We recorded again different reference spectra of all oxidation states of the selenium, going to also to higher oxidation states. We also, and which is often very important, you might know that much better than me, that the right reference compound or having the right reference compound available makes the comparison much easier. And so we also investigated the organic seleno compounds. We made some Athena fitting at this time, and what came out can you see here in the table. So if you look at the selenium-enriched button mushrooms, you see most part of the selenium is connected to the cysteine, a lower part to the methionine, and there's some remaining selenite when feeding the mushrooms, which means that you put some selenite in the soil and then cultivating the mushrooms. If you look at the results for the selenium yeast, Saccharomyces cerevisiae, it's a typical baker's yeast, which we use, then you see it in another order. You see also selenium connected to the cysteine, but the main part is connected to the methionine and also some remaining selenite in this one. So what does it mean? And now I come to the questions, what is the best biological form which can be used by human beings? That is selenium connected to the cysteine and not to the methionine. So if you eat those dietary supplements based on a yeast basis, then there's of course some selenium which you can uptake, but the second best is only the methionine, but this dominates in the yeast. So it is not the best form. So first learning is eat fresh mushrooms and not selenized yeast if you want to add some selenium. But an interesting thing is, at this time, selenium cysteine, which is the best biological form, which you can eat with mushrooms, which is fine, everything is okay, is not listed in the EU law. Probably forgotten, but allowed and obvious occurring in mushrooms and partly in selenized yeast. So lawyers and EU officials, they should follow X-rays and scientists. That was the finding, and this was a connection, as I promised you, together what Susanne von Ameln did when looking in the EU law. So that is also, I think, an example where you convince people from totally other fields that synchrotron radiation might be a good idea to use. Okay, thank you for attention. Yeah, thank you.
Okay, thank you very much for your presentation, Professor Prank and Professor Holmes. Is there any questions for this presentation? I fully agree with the experience that you show us. I mean, this is the same experience that we have at Alba. I mean, it's 100% equal. Yeah. And thank you for the selenium. I mean, we have some studies also on selenium in our absorption bill line.
In wheat, yes?
Yes, and it's a collaboration with the University Autónoma of Barcelona. I mean, this is the nearby university, so it's good to know that these kind of things are happening the same.
We can sell it as a joint preliminary work for the next proposal for the
exactly. So there is a good ground for future collaboration.
Yeah. Okay, thank you.
But it's very interesting, and how this apply to the industry and in this case to the agriculture. I mean, how to grow more healthy food that can help us to. Because if I understood well, also the selenium is very good for the heart. I mean, for so it's good for the blood circulation and for the heart in general. So it's a good element. Okay.
Okay. Thank you.
Thank you.